Welcome back, everybody. We're gonna get started. We've got one more great speaker and one more exciting panel for you. Our next speaker is Greg Kregoski from Rohde and Schwarz, and Greg is at the Automotive segment manager there, This is correct. All right. So, Greg, I'll turn it over to you. Looking forward to your talk.
Thank you. Can everyone hear me? Great. So this topic is kind of an in-depth topic, and I've changed the title slightly from what you see in your brochure, but it's Automotive Radar Testing of FMCW, Frequency Modulated Continuous Wave. Trying to talk and teach about FMCW in 20 minutes, it's kind of like trying to eat an Austin burrito in 5 minutes, but I did it for lunch today. So I think I can do this too, get through this. All right. So, automotive radar is one of many sensors in a car, and it's part of the overall topic of ADAS, Advanced Driver Assistance System. So if we look at some of the sensors that are in a car that are being used for ADAS, it's some of these that you can look at right now. There is cameras, ultrasonic, which are used typically for parking. They're short range, and they're really inexpensive, and they're cheap. And if you look at the bumpers of your new cars, you see those little dots around the perimeter of the front and the rear bumper. That is typically your ultrasonic sensor. There's LiDAR, which can be used for long range. There's a lot of resolution in LiDAR. That's light detection and ranging. The problem with LiDAR is that it can be quite expensive, and on top of that, it's susceptible to bad weather conditions like fog and rain. So it's not a one type of technology that fixes everything, although some people who support LiDAR like to believe that it is. It's not. It's far from it. Cameras. Cameras are great because you put a camera around the car. You don't even need a computer to analyze what's happening on the camera if you don't want to. You could display the outside view of the car from a camera to the driver inside the car, and he'll understand or she'll understand exactly what he or she sees. And cameras are relatively cheap, but they have their challenges as well. So if you are using a camera as part of an anti-collision system, hypothetically, that camera has to react fairly quickly when it goes from severe light to severe dark conditions. For example, going from a dark tunnel to bright sunlight or vice versa. So in order to get that sensor dynamic range, you would need something like an HDR, high dynamic range camera. And those are not inexpensive. In addition, you have to be worried about that sensor response time as well. But today's topic that I'm talking about are radars. And radars are good for a lot of things. Short range and long range. They can see through bad weather conditions. They can see through certain types of objects. The only negative about radars really is the fact that they take a lot of computational power to determine what the radar is actually seeing. And we'll talk more about that specifically in today's presentation. If we look at the US frequency allocation chart and ask ourselves where are the frequencies for automotive radar today, they're typically in two frequencies, 24 gigahertz, that band, and 77 gigahertz. But the 24 gigahertz band has a couple of negatives to it. It's in the IMS band, which means you're limited to how much bandwidth you can actually use. And for all practical purposes, you're limited to about 250 megahertz or so. And one thing that we're going to discover today in this discussion is that the bandwidth of FMCW, the bandwidth of the chirp, is what determines the range resolution or the ability to determine two different targets that might be covered by one chirp. So there's a limitation of 250 megahertz. In addition, that band will be closed down in Europe, I hear, in the future. So let's just turn that off for today and talk about 77 gigahertz. So what are the pros of 77 gigahertz? First of all, there's ample bandwidth. I just mentioned that. So the 77 gigahertz band goes about from 76 to 81. Don't ask me why it's called 77 and not 79. But it goes from about 76 to 81. So you have a nice wide bandwidth. And that wide bandwidth gives you the ability, again, to do great range resolution. So that's one advantage. Another advantage is that it attenuates quickly in the atmosphere. Why would that be a good thing? Why would you want anything to attenuate fast when you're looking out in the distance for a target? Well, it's because if it didn't attenuate fast, you'd have Austin and Houston bouncing radar beams off of each other, and you wouldn't be able to discern these billions of radar transmissions that are reflecting off of everywhere. So this is actually a positive thing, the fact that it attenuates relatively quickly. And it requires smaller components than 24 gigahertz. So 77 gigahertz is about 3 times higher than 24 gigahertz. That means the components required are roughly 3 times smaller, 1/3 the size. That's a good thing because that means you can place more of them around the perimeter of a car and put them in places that you couldn't put them before. All a good thing. But before we get into FMCW, we have to talk about pulsed radar first. And pulsed radar, the way that I think about it, is nothing more than a CW modulated signal that's turned on for a short period of time and it's turned off as you listen. And it's turned on and it's turned off. Whereas FMCW, by the definition, is a continuous wave. It's always on. It's always ramped up or ramping down, but it's always on. So let's compare the two. Oh, by the way, go back one slide. If you look at on the right-hand side of the slide, FMCW is represented this way, amplitude versus time, but nobody looks at a chirp in this fashion. They always look at time versus frequency. And that I refer to as the chirp. And of course, if you take that RF frequency and take it down to the audible band, if you played it, it would sound like chirp, chirp. So that's why we call it a chirp. Okay, ranging, pulse radar. How does that work? It's pretty simple. You send out a pulse. T0 marks the spot where the energy is first transmitted, that very sharp edge. Travels out to the target and hits the target. That's called T1. So assuming that T0 is 0, then the time to get from the transmitter to the target is T1. Time to get back is 2 times T1. So the round trip time is 2 times T1. Let's call that tau. So going back to your basic, is it middle school or high school when you learn this? I forget. But range equals rate times time. So your rate of the speed of light is 299 and some meters per second, million meters per second. And your time is tau over 2, where tau represents that two-way transit time. So we only want the one-way time. That's why we divide it by 2. So it's pretty simple to figure out, right? It's not rocket science. I give it a green check because it's easy to use basic math to figure this out. Now let's compare it with FMCW. Range equals rate times time. Does anybody know where T0 is located in this case? There is no starting pulse. There's no end to the pulse, because it's on, by definition, continuously. It's a continuous wave. So to figure out the ranging, you have to do some other type of math and figure this out indirectly, and that's kind of cumbersome, so I gave it a red check mark. We'll come back to that, by the way. Range resolution, again, pulsed radar. If you look at the picture on the left-hand side, you see a pulse of a certain width hitting 2 targets, and that pulse is narrow enough such that it can delineate between the 2 targets. In other words, those targets are spaced far enough away. And so you see 2 reflections coming back. But on the right-hand side, you see 2 targets that are relatively close to one another, and that pulse width is too large, so you see 1 reflection. How do you correct that problem on the right-hand side? That's easy. Just narrow the width of the pulse, right? And then it enables you to have more delineation and resolution and range. Pretty easy stuff. Range resolution in FMCW. Range equals, or the delta range, range resolution equals rate times pulse width. What is your pulse width? Where's the edge of the pulse? There is no edge of the pulse because by definition, it's continuous wave. Don't like that, I give it a red X. Now I mentioned that you have to figure out range and range resolution indirectly using FMCW because you're constantly transmitting. It doesn't stop. So while you're transmitting, you're also constantly listening and doing something in the background computationally wise to figure out what's going on. So from a computational intensive perspective, pulse radar is much easier. FMCW is not, so I gave it a red X. All right, so clearly pulse is better for ranging, range resolution, and it uses less computational power. So the winner for automotive radar is, everybody say it. Oh, whoa. That's interesting. We have a mix of opinions. The winner is FMCW. How can that possibly be? Well, we'll take a look at that right now. Pulse radar does have some downsides. On the left-hand side of this slide, you see the time domain of a pulse and an FMCW chirp, and on the right-hand side, you see the spectrum domain. So on the left-hand side on the pulse radar, the pulse is on for a short amount of time, which means it's surrounded by an envelope, which is really, really tight. We want the sides of that envelope to be almost like a brick wall. So it goes on and then it's off instantaneously. So if you think back to your FFT or your Fourier analysis days, to make a really sharp edge signal, you have to mix a whole bunch of sine waves together, a whole bunch of frequencies. So the frequencies or the spectrum spread and creating a pulse is actually quite large. Don't be deceived by the width of the pulse, that little skinny width on the right-hand side, that's not what we're looking at. We're looking at the width of the pulse as it spreads down toward the floor. It's wide. But if you look at FMCW, you might look at that first sight and say, well, that's really wider. It's only meant to be a comparison for concept. Notice how clean it is once it breaks down at the very bottom. So the pulse width of FM modulation is actually narrower than doing pulse modulation. So, downsides of pulse, it's got a wider bandwidth. It has higher power requirements. Why would it need higher power requirements? Well, in FMCW, you're continuously broadcasting, but on pulsed radar, your pulse is on only for a moment. So the average power over the pulse repetition interval is relatively small because your pulse is on just that long and you're off that long because you're listening. So your average power is low. No problem, let's jack up the power. So let's increase that pulse by 10 times its amplitude. That works, unless of course there's a pedestrian looking at you in front of your bumper, in which case that's a bad thing. So you cannot transmit too much power because of the potential damage you can do to those around you in automotive radar. You need a lower power or a higher average power using some other technique, and that's what FMCW is all about. Also, notice that I said earlier you can't listen while you transmit and pulse radar. That's true. So your pulse is on for a short amount of time, and you listen for a long time, so your duty cycle is really low as well. So there are some upsides to FMCW, and that's exactly why automotive companies are using FMCW. Whole bunch of use cases for FMCW. The one that we're going to look at today is the one that I've circled in a square. So most of these are probably obvious. You can determine range, you can determine velocity, you can look at the target size, you can look at angle of arrival and even some other things. But we'll talk just about this today because we're limited on time. And notice that I'm, pointing to that thing called FB1. That's called the beat frequency. I'm going to talk more about that right now. So when you transmit a pulse represented by the blue slope, that blue slope, and by the way, notice that it's not amplitude versus time, it's frequency versus time because it's a chirp. So as you increase that frequency, it goes up in slope over a certain amount of time, and then the reflection of that FMCW broadcast pulse is the green reflection. Tau, remember tau from the first or second slide? Tau is the two-way transit time, or any time, we don't care if it's two-way or one-way, but it's transit time of that pulse or that energy from the target back. But we can't calculate tau directly because we have no edge. Remember that? There is no pulse edge in FMCW. So we have to calculate this indirectly, and we do so by calculating, or measuring, I should say, the beat frequency between the original signal and the return signal. And it turns out that there's actually two beat frequencies, one that represents the range, and if you have motion, one that represents the velocity as well. So this is an indirect method of calculating range and velocity by measuring the beat frequency. Now, there's different types of various types of FMCW waveforms. I've only shown 4 here. There's dozens of types. There's slow chirp, which basically means you're looking at, in this case, a triangle ramp, and it's over what we call a CPI, a coherent processing interval, basically the time on target that you're pointing the beam or the energy toward the target. So basically, in the case of the ramp, there's 2 CPIs. There's one for the upslope and one for the downslope. It's a relatively slow measurement, and the green triangle is the reflection. Multi-slope with slow chirp is the same thing, except now we add additional slopes. Why would you ever need to add additional slopes? Because in the case of a moving target, you can actually have ghosts that are created from the actual target. So to get rid of those ghosts, you basically use a third slope, and then mathematically that pulls the real targets out of the false targets. There's something called fast chirp. So instead of sending one slope in one coherent processing interval, we can send 50 slopes or 50 sawtooths in one coherent processing interval. This does the same thing in essence as the ramp, except that it does it a lot faster. So if it's a lot faster, why don't we just use this all the time anyway? And the answer is because it takes more processing power to do the picture in the lower left-hand corner. So automotive companies are relatively price conscious, and they don't necessarily want to put these types of high-performing radars everywhere on the perimeter of a car. Another technique called fast MFSK, multi-frequency shift keying. All I want you to look at is that there's various types and recognize one thing. What's common in the FMCW waveforms? A chirp. And there's something about that chirp. It better be a straight line. Why does it have to be linear? Because you're not measuring time directly to calculate the range and the velocity. You're actually measuring the beat frequency difference between the ramp that you transmit and the ramp that you receive. So anywhere along those 2 lines, they better be parallel. And this are things that are kind of funny in FMCW. They're not always parallel. So if we zoom in a little bit closer and see these two waveforms, these two chirps, one is a transmit chirp in the blue and the one is green is receive. Look at the black arrows between the two if we have oscillations on that chirp, which by the way is not necessarily that unusual. These two black lines, if you measure them, trust me, I did, they're the same. But one is incorrect. So to correct that, you have to add that little red arrow. In other words, the beat frequency for range and velocity of the arrow on the left is greater than that on the right. What does that mean? Cars crash. So nonlinearities will ultimately result in accidents because it'll give you a false positive on what you think or what the car thinks the range and the velocity is. So linearity in FMCW is a critical measurement that you have to take care of. How do we measure linearity? Of course, being from Rohde and Schwarz, I'm going to show one of our analyzers. So we have this analyzer, by the way, out in our booth outside the hallway here. This is the FSW 85. It's a spectrum and a signal analyzer that allows you to load certain personalities onto it to do different measurements, whatever those measurements happen to be. Could be Wi-Fi, could be LTE. In the case of this example, it's basically something that we call K60. It's a transient and chirp analysis piece of firmware. And what we're looking at is the linearity of the chirp, the length of the chirp. Is it linear from chirp to chirp or just on one chirp? And then dozens of other types of things. But basically, you take a product like this, and you can feed that directly into this analyzer. Now, some people who are measuring FMCW want to measure it in what I call the native domain. They don't want to down convert it to something. They want to measure it at the actual millimeter wave frequency of 24, or in this case, 77 gigahertz. So with a product like the FSW, you can do it as it goes up to 85 gigahertz. And if we take a look at some of the measurements that we're making inside the analyzer, there's a spectrogram of the waterfall. Basically, it's a time domain, not a time domain, but a time stamp of continuous chirps over time, so you can see if each of those chirps over time is comparable to the chirp before it and the chirp after it. In other words, is there consistency in the behavior of the product or the sensor over time? Or, if you want to look at it in a more intuitive way, you can look at the chirp itself. In this case, it happens to be a triangle plot. Or, if you want to take a look at the chirp length, which is, again, not necessarily defined by time, but defined by frequency, you can look over the entire length of that chirp to see what it looks like, either the entire chirp or pieces of the chirp itself, to see what the distribution is. Is it truly linear or not? And of course, there's tables that we collect inside the analyzer to monitor the chirp performance. So you can do a long-term chirp test, not just over the course of 10 milliseconds, but you can do it over the course of an evening if you wanted to see how your device under test operates in the presence of cold and heat and everything else that might be subjected to. We okay time-wise so far? Perfect. All right. Again, big topic. I went over this very quickly today. On YouTube, there's a number of videos that we offer that tell you more about FMCW radar measurements, pulse radar measurements, and many other types of radar measurements as well. But I would encourage you to look at YouTube, some great educational content there. We also have some of these application notes on the table in the back. All right, so let's sum this up. FMCW is preferred over pulse radar for automotive applications for the reasons we discussed earlier, despite the fact that the illusion might be that pulse radar is better initially, at least from the outset. Range and velocity are calculated indirectly using FMCW. It's not a direct mathematical measurement. So we use beat frequencies to do that. The linearity of the transmit signal is critical to determining correct ranges and velocities of the target that you're measuring. And I mentioned 4 FMCW waveforms on an earlier slide. There's actually dozens. And what's getting really complicated about this whole topic is it's not just FMCW anymore, although there's still a lot of FMCW in play with radars. But there's very complex waveforms, even things using polyphase coding and compressed pulse signals. It's becoming very complicated and very expensive to even be able to test these scenarios where these tier ones are providing these sophisticated levels of radar systems that are able to look at anything and distance and range resolution maximized at the same time. More complex waveforms are being developed. I just mentioned that. And of course, most important thing is radar is your friend, unless of course it's being pointed at you as by a police officer. Other than that, I think that's close of the material. Any questions?
Go ahead and take a couple of questions.
Tesla just announced that they improved their radar capability
I can tell you what I know, and I won't tell you other things that I might know, but I can tell you what I know that I read in the paper. And by the way, they're one of our customers, as you can imagine. But initially, when they were using radar almost exclusively looking out of the front for object detection, the problem was the elevation angle of the beam was too wide. So they basically reduced the elevation angle, and they replaced the top portion of the elevation with a camera. And the camera couldn't handle the dynamic range, as I mentioned earlier, like they thought it could. So when it saw the side of a truck, which was pure white, it mistook that for sky, basically drove the car right under the truck. And of course, that was the end of that. But what I can tell you is that every OEM and every Tier 1 that I've worked with, every single one without fail, is either already using radar as one of those sensors that I mentioned earlier, or they've already come to the conclusion that they have to move to radar. They can't just depend on LiDAR and cameras.
Greg, another quick question
Sure.
from me. These waveforms, even the more complex ones, except I don't understand much about the polyphase ones, but the FMCW waveforms are so simple that they would be easy to falsify. So if you pull in the, if you had one of your measurement units and were able to notice what kind of broadcast was coming off the car behind you, couldn't you just gin up a response that was fictitious? And are people thinking about the security aspects of this?
Yeah, so yes, you could falsify one. You could spoof it into thinking it's seeing something else. And of just equal concern is not the fact that somebody might be intentionally spoofing it, but the fact that once you start getting 100, 300, 1,000, 4,000 cars all transmitting concurrently in a city, how do you pull out the right signal that you need to look at? So yes, the security topic it's of great significance. It's growing logarithmically in concern. I'm not an expert on the topic, I can tell you that, but I can tell you that we do have experts in our company who are beginning to look at that very closely.
Okay, let's thank Greg.
Oh, thanks.
I'd like to invite the panelists for the final panel up to